Well, good afternoon, folks. My name's Roger. I'd like to welcome you to the gathering this afternoon. We're going to talk about basic rules for designing a solar energy system. Let sun make a little bit of electricity, maybe a lot. Um, we've got manageable group this afternoon, and when that happens, and I don't mean that as an April Fool's or anything. It's nice to have an idea of exactly who's sitting in on the webinar and a little idea on background. Um, Personally, I'm a retired electrical engineering professor, but I've been involved in renewable energy and energy efficiency things since 1975 when the first oil embargo took place. And so I've been around for a little while, followed the solar up through solar water heating and photovoltaics and things like that. And in the last 5 years, I've been working for a former student. I've done final checks on around 70 megawatts worth of residential rooftop PV systems. So I've got a fairly decent familiarity with what's going on out there right now. And so with that as an intro, let me ask, this will give you a chance to make sure you know how to open your mics because we're going to uh, set it up this afternoon so that if you have a question, you just open your mic and ask it. I don't think that's going to be as bad as a dinner table conversation or with 10 people around the table. Uh, and if it gets unmanageable, we'll figure out a way to fix it. But I don't see that as going to be a problem. So let's start with Christopher. Christopher, where are you joining us from, and what's your basic background? What's your day-to-day pastime? And while Christopher is looking for how to turn on his mic, Ed and Peter and Sylvie and Tom, if you do the same thing, so when it's your turn, you can jump right in and fill us in on what's going on. In fact, let's give, there you go, Christopher. I see your microphone muted. Let's unmute and tell us a little about where you joining us from. Well, while Christopher is working on it, how about you, Ed? Have you, can you turn on your mic and, no, sure.
All right, how
Oh,
about now?
okay, there we go, Ed.
Very good. Uh, I live in Ohio near Toledo. I retired not too long ago, but I'm thinking now about installing some photovoltaics at our home. I was an electrical engineer by training, by school and career, so I'm interested in learning the latest so I can um, get work on a system of our own. And I am a PE, so I'll continue to study to keep up with that. So that's my background. Thanks.
All right, well, Christopher, I hope you'll learn what you need to go out for bids this afternoon or whenever you get a chance to do that. And
Yep, hope
Ed,
so.
how about you? I see your mic is showing on my screen now.
Yeah,
So,
I don't know who you mentioned. This is Chris Hashak. I'm also I'm a mechanical engineer I'm in Purchase, New York, which is Westchester. Uh, I've been a mechanical engineer a while. Yeah, I'm in the retirement age as well.
okay. Well, I'll admit to being in retirement age as well. I'm 82. Got a great grandson who's hoping I do the right thing. Peter, how about you? And then Sylvia, you'll be next, and then you, Thomas. What can you tell us about, okay, here we go.
Hello, everyone. My name is Sylvie. I am not sure. Like, there is so much echo. I don't know if it's from my side. I,
Um, Depending how many people have their microphones on, it could be some echo from mine. Let me turn my audio off and let's try it again.
So I don't know
okay.
if you guys can hear me, but I had a similar issue a minute ago. And what had happened is my Zoom call opened in the browser and in the app. So
Mm.
I had Zoom open twice, and that was causing a lot of echo. I closed one of those, and that fixed it.
Oh, you're right. This might be my situation. Okay, I'll try to fix that. Okay, until then, my name is Sylvie. I am from Toronto, Canada. I am. I haven't worked with photovoltaic system before, so I thought it would be a good opportunity.
Sylvia, what's your background? What
Electric,
discipline?
sorry, electrical engineer.
Okay. And I see Amir's here. How about Thomas? Sylvia, I see your mic is on. Thomas, are you ready? Can you tell us about yourself? Okay, almost. No, no, your mic is on. I don't know. I don't hear any volume, though. Okay, well, folks, let's get started. Oh, I see a few chat messages. There might be some information here. Let me just click on the chat box and see what's happening here. Uh, okay, okay. How to unmute? You click on the mic is how you click on it, or how you unmute. And I'll be asking a few more questions as we go along, so we can pick up on that. But let's get started. A fair amount of material here because the whole idea, we're talking about the essentials of photovoltaic system design, which means we want to talk about everything. And that's a bit of a challenge in 2 hours, but this material you see today is the essence of what is needed to install a way of reducing your electric bill and perhaps making your system more reliable in the event there might be an outage, as long as you then follow up and figure out how to add some batteries, which we are not going to do today. Okay, but let's get started and move on from here. Um, so, first question is, can we afford it? Is it PV it's pretty must be expensive. But let's take a look and see how expensive it really is now. Um, Back in 1975, it was kind of expensive. If you wanted to buy a watt's worth of photovoltaic uh, cell, it was going to cost you over $100. But if you do that now, 2024, 25, 26, it will cost you 500 times less. Now, what else is out there that is only 1/500th of the cost of 1975? Not much, not much at all. So, given that, because the prices come down because of a lot of reasons, because mass production, improved technology, all kinds of things. And in fact, now this is in real dollars as opposed to inflated dollars. So if we take that into account, the probably costs are up by a factor of 10. This could be down by a factor of 5,000 corrected for inflation. So, I mean, the number is unbelievable, and that holds a lot for a lot of electronic type things. I mean, look at television sets and other things that are relatively inexpensive, and compared to other things, where the cost is going up. So, in any case, this one fact alone, plus the fact that things are becoming more reliable, and a lot of other things, means that if we compare different energy sources using the so-called levelized cost of energy concept, what we end up with is the following. And what levelized cost of energy is basically adding up the total cost of the production of the energy, starting from building the source to adding the fuel, burning the fuel, maintaining the source, and decommissioning at the end of life. And after you take all those costs into account, and then divide by the total amount of electricity produced, and then take into account the time value of money, gets to sound pretty simple, doesn't it? You come up with a number in cents per kilowatt hour or dollars per megawatt hour, depending on what units you use. And these are the numbers for various sources of energy as of 2024. Combined cycle dispatchable power, 3.75 cents a kilowatt hour cost to produce. This is the levelized cost of electricity. This is what you need to sell it for in order to get back your initial investment. Onshore wind, 3.78 cents per kilowatt hour to get your initial investment back. All right. Standalone photovoltaics, 3.35 cents per kilowatt hour. Now this is standalone photovoltaics, you notice, and that's if you have a utility independent system, standalone PV, 3.35 cents a kilowatt hour, not bad. If you just have plain old PV with storage, then you got 5.47. This is with lots of storage. You know what? I think standalone means PV without, I hadn't even thought of this before. I believe what we're talking about is PV only without batteries. That's the only reasonable interpretation of this number, and I don't know why they called it standalone PV. So let me correct myself on that. Standalone PV is a grid-connected system with no batteries. That's a number that's much more consistent. Okay, and this isn't a large-scale system. Home system, residential solar, more like 6 cents, and if we and then there's geothermal, 3.74 cents. So these are the kind of modern stuff that's out there and coming geothermal special. I read an article this morning how the folks are getting pretty excited about going larger scale. So we're talking about systems here that are expected to be completed by the end of 2027. This is the estimate made. Now, one important thing here is these estimates are based on the so-called load factor. In other words, what fraction of the total possible energy they could produce if they're running full tilt 100% of the time versus the total amount they actually produce. Because most sources don't run at full speed all the time. Closest to that is probably nuclear because it has to run at full speed. Otherwise, it either stops or it melts down. And but most of the other energy sources, they turn on when they need them. So nuclear is at one end where there are times when it produces additional electricity that in the past has not really been needed, and they ended up pumping it, using it to pump water uphill, just so they didn't have to cycle down the plant. Onshore wind at 3.78, grid connected, no battery PV 3.35 at the industrial scale. Residential PV around 6 cents, somewhere to 8 cents, and geothermal 3.74, utility scale photovoltaics with storage, that's the 5.47. So that means we're talking about economically feasible, sensible operations. If we include externalities, as is urged by a lot of folks who are concerned about climate change, the externalities being the idea that the carbon dioxide release, the nitrogen oxides, sulfur oxides, acid rain, um, degradation of buildings, all kinds of things like that. Some of these fuels, any of the fossil fuels, would have to have an additional fairly large number that would almost double the figure. Those costs were included in the cost here. Anyway, so bottom line is photovoltaics is very, very much competitive with what's out there, and therefore it makes sense to consider installing it. The other thing that people tend to think about with energy sources is, do you get back as much energy from it as you put into the creation of it in the first place? And where this first had become fairly noticeable was with ethanol, where we made gasoline by using alcohol from plants, and the amount of energy used to make that turned out to be almost the same as what you got back from it when you burned it. So that is not necessarily a very good investment. So in any case, the energy return on investment, if it's greater than one, that means if your solar panel will generate 2 kWh for 1 kWh that is expended in creating it and installing it, then it's a good investment. So here's the numbers, okay? The energy produced over a cell lifetime, the energy used to manufacture the cells, and in 2024, these numbers were somewhere between 10 and 45, depending on technology and where you located it. So the energy payback time then is about 3 years. It takes about 3 years to make as much energy as it took to create the system and install it in the first place. And then for the next 25 to 30 years, your system is going to operate. And so the rest of it is the energy has been paid back in the first 3 years. And one of the reasons the prices are falling is because this energy return on investment is increasing as the technologies improve. And the reason for that is the production of cells and modules is becoming more efficient. That's not surprising. That's what we do. We keep on working on new technologies to make things work better. Cells themselves are becoming more efficient. There are reports now that the current most cost-effective cells out there are roughly 22% efficient. They're the crystalline silicon cells. But there are new cells called the silicon perovskite combination cell, multi-layer, that is, they're now reporting commercially creatable cells at efficiency in the neighborhood of 30%. So that means you can make 50% more energy in the same space. That's very convenient when you're talking about rooftop solar or wherever else you might put it, that you can make 50% more energy because your cells themselves are more efficient. So we're talking background material here. The rest of the system energy costs are also decreasing. As the new technologies continue to come online, and that's in terms of batteries as well. We're not going to be talking about batteries today. I have a separate 2-hour session on batteries for those who may be interested. I'm sure our hosts will be scheduling that one relatively soon as well for anyone who wants to follow up. So, what are the types of photovoltaic systems out there? Well, there's basically two types. There's standalones where they just sit there all by themselves, not connected to the grid. They make their electricity. They have some batteries. They store it for nighttime if you need it. If you don't, then you just make it while you use it. But that's standalone when there's no connection to the grid. And the grid connected is when it converts the DC electricity from the sun into AC electricity that goes to the grid. Okay? So now there's several different versions of grid-connected systems, several different versions of standalone, but that's the main difference between the two types of system. Either it's connected to the utility or it's not. Might be a roadside sign, for example. Here's a standalone system out in Nevada because it's way out in the boondocks out of a national park out there, where the building here is the building that's the visitor center. And they're making enough electricity there to run the lights and things in that building. Here's a pretty simple standalone system, weather station in Utah, uh, a road crossing sign in Wyoming, that same crossing, next crossing sign in road, that same sign in Wyoming a few seconds later after it changed the message that you better watch out for those big game out there. More examples up in Massachusetts, rooftop PV. Notice a pretty significant slope on that top roof to keep the snow off. But that's also a pretty good slope. Notice also, though, they're looking in two different directions. That was unheard of 25 years ago. 25 years ago, everything had to look south. That's no longer the case. It is now cost effective in Florida and most other places with modules that look east and west as well at a cost of maybe a 20% loss in the amount of electricity that it would make. But then again, that simply means that you'd have to charge about 25% more for the electricity that you make with it. And if that's still less than what you're paying for the electricity from the utility, it's still worth it. And down here in Florida, it's no big deal to have east and west facing. Much better to face east without a big tree in the way. And even in some cases, north facing, as long as the slope isn't too big, even though you have almost a 30% loss on the year, summertime, when the sun comes up in the northeast and sets in the northwest, you can get a fair amount of production early in the morning and late in the afternoon, which are sometimes the time when you want that electricity. So you don't even rule out north facing sometimes, depending on the application. So, and then there's our friends up in Yellowknife, Northwest Territories. I don't know if any of you have been up there, but this is a wonderful place to go. Take a boat ride on the Yellowknife River and you get a picture of this house. These folks are pretty much on their own with solar. Probably have a gasoline generator, but they're making as much as they can with the sun. And so therefore, geographically, there's not any particular limit either. There's systems in Alaska. In summertime in Alaska, there's a lot of sunshine. So, no, not so good in the winter. Nice to have a little geothermal or something else in the winter. But in any case, then these are fairly old systems. These are 15, 20 years old, maybe more. And they were still installing them then because it was worth their while to make that extra electricity. I doubt you'll find any systems like that in the United States. Most of the codes are going to say, no, you don't dare do that. They're going to blow away on you. But I thought it was kind of a pretty picture when I took it, so I want to make sure everybody had a chance to see it. Here's a nice commercial installation. Notice that these modules don't have very much of a tilt, do they? And the reason is you can put a whole lot more on a roof if you don't tilt them very much. And the loss in production for a 5-degree tilt versus a tilt at latitude is made up for by the fact that you can put more modules up there and you can still make more total energy, more total kilowatt hours by putting them closer together at a shallower slope. So, and furthermore, at a shallower slope like this, less than 5 degrees, the wind load is smaller. So that's always a nice thing to realize, especially in a place like Florida. Here is your utility scale out in the field, and these are a slightly older system because they're tilted at an angle to produce a lot of electricity, but that way they have to be spaced a little further apart so the front row doesn't shade the next row, and so on and so on and so forth. These are fixed mounts. There are also some very interesting tracking mounts and so forth. So the mounting systems themselves, you could spend almost a full day just talking about different ways of mounting these things. We're going to spend some time. So those of you who are mechanical engineers will be happy to hear some mechanical terminology here. And the electrical folks should hear that terminology anyway, because it's all very similar to the kind of electrical stuff we talk about. Let's start then. I guess we already started, but to begin with, let's take a look at what we can get from the sun. The peak sun intensity is 1,000 watts per square meter. Now that's if you are directly underneath that sun and it's shining straight down on you. And of course, that doesn't normally happen. First of all, you'd have to be somewhere between the two Tropic of Cancer and the Tropic of Capricorn. Otherwise, if you're not in the tropics, the sun is never overhead. So therefore, the peak sun intensity is 1,000 watts per square meter. Up at the top of the atmosphere, it's about 1,367 watts per square meter. So that means the atmosphere absorbs it, and it means the more atmosphere the sun goes through, such as at an angle, it means that rather than 1,000 watts per square meter impinging on that solar panel, you're more likely going to be seeing 800, 700, 600, 500 watts per square meter. So the actual watts per square meter is not nearly as relevant as the estimation of how many kilowatt hours of electricity can be made by a given, say, 1,000 watts of solar panels in a day's worth of exposure to sunlight. Now, of this 1,000 watts per square meter that might be available, about 20% of it can be converted to electricity, as we mentioned earlier, by the solar cells themselves. The other 80% turns into heat. Some of it is reflected. So it's not really turning into heat necessarily. Some are reflected, maybe 5%. So that leaves about 30% to turn into heat. The annual conversion range. In other words, how many kilowatt hours per year can you get for every kilowatt you install? And it typically ranges from 1,000 to 2,000, depending on the system and exactly how it's mounted, what the direction it's facing, what's the slope, and so forth. There are computer programs. People have done this modeling. They've done lots and lots of empirical measurements on sunlight. So there are a number of different programs available to model the system. Let's say you're going to have a system that's tilted at 25 degrees facing southwest, and you're in Albany, New York. You can then put that information into the computer program, and by the time you blink your eyes, it tells you, it analyzes on an 8,760 hour per year basis of how much electricity it's going to make. And surprisingly enough, it tells you it's not going to make anything at night. Okay, so, and these are those models I've been telling you about. Okay, the electrical properties of the module itself, the output power, the output current of this module is almost directly proportional to the intensity of the sunlight. So at a given voltage, the amount of power that's going to come out is going to be almost directly proportional to the amount of sunlight, as you can see from this graph. Notice, though, that there's a point where all of a sudden that almost constant current starts tailing off, and all of a sudden there is no more current flowing at a certain voltage. That voltage is called the open circuit voltage. So if you've got a module that has leads on it and they're not connected to anything, and you point it toward the sun and you connect your voltmeter across it and measure the DC voltage, you will measure the open circuit voltage. 25 years ago, this was commonly done by the field installers because the uniformity from module to module was usually within about 10%. Uniformity these days is less than almost 1%. So nobody worries about that anymore. If you've got a 435 watt module, then that's what it's either going to be somewhere between 430 and 435. Or sorry, if you have a 430 watt module, it'll be somewhere between 430 and 435. And if it's 435, then it's going to be rated as a 435 watt module. So therefore, we don't have to sort through things these days. You simply assume that these modules are sufficiently identical that we can treat them that way. And that's, again, that's part of the improvement in manufacturing technology. So notice that we have this point here, VM and IM, meaning that's the maximum power voltage, maximum power current. This particular module, if we operated at that point, that voltage and that current, which as you see is a little bit right around 11 amps and somewhere around 42, 41 volts, if you multiply 41 times 11, then you get 451 watts. So this is about a 450 watt module here at standard test conditions. And fortunately, the technology is out there that the inverters themselves that convert and the charge controllers and any of the other electronics that these modules feed into, these can be designed to operate the modules at their maximum power point. And why would you not want to do that since the power they're getting from the sun is free anyway? The only reason you wouldn't want to do that would be if there's nowhere for that power to go. And obviously, if you're operating at a certain power level, then that power has to be used somewhere. So there are four parameters that characterize these modules. A short circuit voltage, you can see where those are, somewhere up in the 46 to or 40, 48 to 47 to 50 volt range. And open circuit or short circuit current, which is that means there's 0 volts across it. If you short the two module leads together, the module won't blow up. It'll simply have a certain amount of current going through it, and the voltage times the current. In fact, the matter is it delivers 0 power, which isn't quite true because it's not totally uniform and there will be some power dissipated in the module, but it does not damage the module if you short it out. Try that with your generator, your gasoline generator, or almost any other electrical source. Try shorting it out, you're going to blow a fuse. But not with PV. They are current limited, and it's important to realize that the maximum current depends on the intensity of the light that's shining on them and whether or not they're being operated to produce maximum current. Okay, so these four parameters define the module and are useful in terms of deciding which module you might use in the system you're going to build. All right, if we plot power versus voltage, you can see it much more clearly that the power increases up to now this is not 1,000 watts. the module power there is about 450, but the 1,000, 800, 600, 400, 200 is the number of watts per square meter of sunlight intensity that's shining on the module. So you can see that the power increases almost linearly with respect to the sunlight intensity. It's not quite linearly. They tend to drop off a little bit at lower intensities, but for general analysis, it's good enough to assume that it's pretty much a linear relationship. So these maximum power points are important, and there are things out there called maximum power point trackers. They're electronic devices, and pretty much everything that you connect a module to is going to have a maximum power point circuit in it. These maximum power point trackers, they themselves use a little power, but most of them are about 99% efficient. So losing 1% of power in order to get 100% of the available power, that's a reasonable trade-off. The maximum power is normally, the maximum power point tracking normally takes place in the inverter, but we'll see some systems where that's not, where it takes place at the module itself. Okay, temperature is an important factor as well. Notice that the colder the module gets, the more power it can produce. Why is this? Well, there's some very interesting physics reasons, but the important thing is to notice that, first of all, as the module gets colder, its voltage goes up. And that's important to know because you need to make sure that at the coldest point, the short circuit voltage of this voltage, not the short circuit, the open circuit voltage of this solar module does not exceed the maximum input voltage of whatever piece of electronic equipment it might be connected, because otherwise you'll burn out that piece of equipment. It's more than likely going to be a maximum power point tracker. So your specifications on your equipment will say maximum voltage, maximum input voltage, 80 volts, maximum input voltage, 600 volts, 1,000 volts, 1,500 volts, whatever the voltage might be. It will have that specification. And you need to design your system to make sure that it does not increase to too high of a voltage when it's cold and there's no current being drawn from the system, that open circuit voltage. And that's the sort of thing that generally happens first thing in the morning on a very cold winter day. You notice that the open circuit voltage does not vary a whole lot with sunlight intensity. In fact, it varies logarithmically rather than linearly, whereas the current varies linearly with sunlight intensity. And that's the first approximation. Okay, and that's about 0.36% per degree C. So you want to keep the array cool, and that's why most of the arrays out there are mounted about 6 inches to 8 inches above the roof, so they can cool off with the air blowing underneath them. You can see this fairly significant increase in efficiency if you keep them running cooler. Orientation, here's a story for Albany. And this just gives an assortment of your optimum amount is going to be south facing at a 30-degree tilt. But if we tilt it at 45 degrees facing south, you still only lose 1%. 60 degrees facing south, you lose 7% on the year. This is annual production. Looking southwest, east, even north, the numbers don't drop. You know, vertically south and in Albany, 67%. So you may or may not want to put it on the side of a building, like on a window, because you lose 33% on that. But west and east, 17% loss at a 25-degree tilt. And again, if you're really interested in these numbers, you don't need to memorize them. The host will be happy to send you a PDF copy of these slides for your use, for whatever use you might want to make of them. And they happen to be my own personal property, and I am happy to share them with anybody for whatever use you might want to make. Here's the options for connecting to the grid. You can have a straight grid connect. In other words, we'll show the diagram. So it makes electricity when the sun's shining. If the grid goes down, the system has to disconnect unless the uh, utility has a special arrangement, but at least it's able to sell back to the grid. And there's the battery backup grid connect, and it has all the features of the grid connect system, but also you can power circuits if the grid goes down. And there is a possibility that you could use this battery backup grid connect system as a assist to the grid if you store electricity during maximum production hours between, say, 10 and 2, and then at 6 o'clock, if the utility would like some electricity to meet their demand, their peak demand, it is possible now for them to communicate with your system and arrange for a deal to buy some electricity back from you. Okay? That's on the battery backup systems. They're probably not going to do that with the straight grid connect. That's just going to make whatever electricity it can. Okay. I mean, there are other things can be done with straight grid connect, but we're trying to get to the basics today, and some fancier stuff might be saved for a later time. So if we're going to do it right, then we need to meet all the electrical design performance specs. It better not leak if it's on a roof, and it better not blow away. And fact of the matter is, if you're screwing this thing down with 4-inch leg screws, more than likely those 4-inch leg screws are going to hold that roof decking down and that roof covering down a whole lot better than whatever nails might be pounded into them. So this is one thing folks don't think about. Leaks, the systems are the companies we've worked, the installers that we designed for. We've never heard any of them fussing about leaks. They know how to do it right. The equipment is designed so that it will last for 25 years without leaking. And that's longer than most roofs will last without leaking. So in other words, it's extremely reliable equipment. So it looks good. And of course, the beauty is in the eye of the beholder. If you have a battery backup system and you have electricity during a hurricane, so you've got, hot food and cold beer or whatever, your neighbors are going to all of a sudden decide that those modules on the front of your house that face south really look pretty good. So aesthetically pleasing. On the other hand, if they're sloppily installed, maybe they won't look so nice. So you want to do a nice, neat job of installing. Need to last 25 years because that's the warranties on all this equipment. So therefore, you don't put in cheap screws. You put stainless steel hardware in this stuff so they don't get rusty. And the thing that's happening, beginning to happen more and more, is that the utilities are taking advantage of these systems so that they can, with curtailment and with various load managements, they can help the utility during peak times to meet the load demand. But with batteries, even better. Okay, so if we're going to do this, what are we going to need? Well, need the modules. Need some racking to hold them up. Need a way to mount that racking. We need an inverter that will convert the DC to AC. UL 1741 says that if you're going to make AC electricity with this thing you want to sell to the utility, it better be good AC electricity. It better be utility grade. And not only that, your inverter has to be smart enough to know that if the grid goes down, the inverter has to shut down because we do not like individual power stations feeding the grid. When the grid is down, we have somebody out there trying to fix it. All the wiring, all the disconnects, everything has to be code compliant. The utility connection has to be code compliant. And there has to be some way to shut this system down for a rooftop system in an emergency situation. If somebody wants to run across the roof, then they don't want to be running through any kind of high voltage or current or up and any possibility of getting a shock. Better pull a permit. And you're probably going to have to sign an agreement with the utility so that they will agree to buy back any excess electricity, or your agreement might say that if your system tries to sell electricity back, they don't have to buy it if they don't need it, because then they have to figure out what to do with it. So all sorts of interesting options on this. In any case, these are the things that are part of the preparation, and you need to be aware. So what are the types of straight grid connect systems? That's what we're talking about today. Let's take a look at the time here, make sure we're doing all right. 247, maybe at our step on a little bit. This is a string-fed inverter system. What do you see here? You see a bunch of modules. The top group of 7 are connected in series, and the next group of 7 are connected in series, and then those 2 series strings are connected in parallel. What's the implication here? Well, the implication is that when you connect things in series, they have to have the same current. And when you connect things in parallel, they have to have the same voltage. So therefore, we call these things strings. Some people call them source circuits. But these strings, with 7 module string, that means the open circuit voltage of the 7 modules is going to be the sum of the voltage, open circuit voltages of each of those individual modules, which would normally be simply 7 times the open circuit voltage of one of them, unless one of them is shaded. And then that's going to do some things to it to mess up its output, because if it's shaded, it can't put out the same amount of the power the other ones can, and yet they all have to put out the same current. So that's why that's called balancing the system. You need to make sure that these things are set up so that every module will perform, and in this particular case, put out the same current because they're in series. And if the voltages have to be adjusted, so be it. So we have total current is the sum of the current of the 2 strings. The total voltage is the voltage of either one of the 2 strings. And that's DC, and that's going to the inverter, and that's an inverter, and that's a straight string-fed inverter system. Now, to get the same optimum performance on these, that means each of the modules and each string has to have the exact same exposure to the sun. Yeah, that's an important consideration. There are other systems we'll see, like this one, microinverter system, where you put the inverter right at the location of the module, right behind the module. Notice the way these are connected. These are connected in parallel. The microinverter has its very own maximum power point tracker. So every module, no matter whether it's shaded or otherwise, is going to put out as much possible current as it can, provided that, and its output voltage is going to be locked in at either 240 or 208 volts. So in this case, every module output is going to be the same voltage, 240 volts AC, because of the microinverter, but they'll have differing currents if they have different sunlight exposures. So therefore, the sum of the current in the string is going to be the sum of the currents of the individual microinverters. And so as you can see, in that case, since currents in parallel add, it means you don't have to have the exact same number of modules in a string with microinverters as you do in a straight string-fed inverter system like the one on the left. So then you combine the outputs of these microinverters in a combiner, and then you have a disconnect. And this combiner box is simply going to have some normally they'll have fuses in, but they might have circuit breakers. Well, actually, normally now they're going to have circuit breakers in. Those generally be two pole 20 amp circuit breakers. And they combine them and they monitor it. There'll be a monitoring box in there that can monitor each of the individual modules by a process called either any of the number of ways, wireless or wired communication technologies that are out there. And then it feeds the AC to a distribution panel where the loads on distribution panel get first chance to use that electricity, and anything they don't use is sent back to utility. And that's the case with the string fed on the other side as well. So any questions? Let's see. I see a one up here. Let's see what we got here. Q&A. Let's see what we got. How residential rooftop connected would differ from non-residential? All depends on what you mean by non-residential, and I'm assuming you mean non-residential rooftop. Residential rooftop systems are limited to 600 volts. A commercial system could be run at 1,000 volts. That would be the only difference. You could use either one of these systems, and we have a third one coming up soon that also that the same requirements apply. Is that the answer you were looking for, Sylvie?
Yeah, thank you.
Okay, yeah, and I'm glad you asked that question because well, that's why you're taking this live, so you make sure you have answers to every question. And by the way, if I waited too long to notice that you had that question, feel free to just open your mic and say, "Hey, Roger, hold it a minute. I have to ask you a question." Okay? So thank you so much. And let's look at the third type of system that is also relatively popular. I tell you that of the systems that we design, uh, probably 60 to 70% are microinverter systems. Maybe 15 or 20% are string fed, and the rest of them are this type, the so-called DC optimizer systems. This is a neat type of system as well, because what it does, these optimizers, notice that they're connected in series. So that means the current has to stay the same. So what do? Each optimizer has a maximum power point tracker as a part of its construction. So they optimize the amount of power by way of electronic means that is available from each module. If they all have the same sunlight intensity, then they all have the same amount of power available. But if they have less power or less sunlight, one gets shaded and the other one isn't, then what happens? Well, what happens is that module has to put out the same amount of current as all the other modules are. So then what has to happen? Well, it means that module's voltage is going to go down. So if that module's voltage goes down, then the other module voltages are going to have to go up a little bit because the total voltage of the string is going to have to be the exact same as the total voltage of that other string. Okay? So the inverter itself is the controller for this system. It says, okay, guys, today we're going to run at 400 volts per string. And so optimizers, it's your job to talk to each other and tell me what you're doing. And I will tell you how much current you're going to need to have in order to get that voltage up to 400, based on the amount of sunlight each of you is having. And they carry that conversation on second by second as the sun shines. And as a result, we have a very efficient conversion of the DC from the modules produced directly into a DC that goes through the inverter. Something like 99% of the available DC from the array. And the fact that it's coming down at 400 volts rather than at 240 volts means that power is current time voltage. So the higher the voltage it comes down at, the lower current it needs to come down at, which means you can get by with smaller wire and your losses are lower. So you have to figure all this out in terms of total system costs and figure out which is best. But these are nice systems, okay? They feed DC to the inverter converts it to AC, and runs it through a disconnect to a distribution panel, goes to, and the PUC means point of utility connection. If the utility needs to shut you down, they flip out that switch. If somebody wants to do some maintenance on the inverter is going to have a built-in DC disconnect switch that will shut down the optimizers. And there's another thing that's called rapid shutdown. And the optimizers are smart enough to know that if they get a signal from the inverter, that they simply open the switch and there is no power output at all. It's all just run open circuit at the input to the optimizer. Let's see, is there a question here? Let's see, what did I see? How? Oh, okay, I'm supposed to click done. Okay, there we go. Forgot to click done. So this is the optimizer system. So we now have 3 different systems. So let's design one of each of them. Okay, and let's start by mounting the modules, because no matter which system you're going to use, you need to mount the modules. So we're going to start with some structural stuff here. And as we say, the design starts with the module unless it starts with something else. But you got to start somewhere. This time we'll start with the module. Okay? Oh, did it backwards. First of all, the modules themselves have to be listed properly. In UL 1703 or 61730, 61730-1, or 61730-2, these are 3 listings. The last 2 are international listings because a lot of modules are just shipped all over the world. And now that we've learned that this whole business is a hoax here in the United States, that means that the modules are being sold to those countries who aren't convinced that they're a hoax. Not that we're not still installing a whole lot of commercial PV in this country. Expected we'll install probably more this year than we did last year. But I can tell you the residential business is falling apart because of the getting rid of the incentive programs. But that's all going to change because electric rates are going up, and all of a sudden this levelized cost of electricity is going to be a very attractive number. And when people realize that at 20 cents per kilowatt hour electricity, and I can be making it for 8 cents by modules on my roof with or without a government incentive payment, why, that's 12 cents I save for every kilowatt hour that I use. And even if I sell it back to the utility, if they'll pay me 20 cents a kilowatt hour for it, then my system's going to pay for itself relatively quickly. If they don't pay me 20 cents a kilowatt hour, then maybe I'll give some second thought to putting some batteries and store it in batteries so that I can use it later when and simply have some available at night so I don't have to pay 20 cents a kilowatt hour for nighttime electricity. So the economics are extremely favorable, and we're not doing much in terms of economics here, but believe me, when you look at what you can produce for the price you pay, if you are not totally shaded by trees around your house, if you have anything that has reasonable exposure, it makes good sense to put this system up on your roof. So these are the listings to make sure that they're properly built, and this is the structural requirements. We talked about UL 1741 earlier as being inverter requirements. In addition to the, and then the 1703 are also the electrical properties, but we have thermal properties and we have structural properties on the modules, and you need to make sure that whatever modules you're using will withstand the wind forces and the earthquake forces if you're in such an area. Down here, looking at Miami-Dade County, for example, we're looking at 175-mile-an-hour winds. That's a pretty tough mounting system, but it's not an issue because the calculations are very straightforward using ASCE 722. So when we're going to do a little bit of that. So let's pick a module. Okay. And this is, I mean, you pick some module and they're getting bigger all the time. So the idea of which one we're picking today might be different tomorrow. But point is, you have to start with something. So let's just notice this one is about 6 feet by 3 feet, actually more like 2 meters by 1 meter in size. And about an 18 square foot module. Other common modules out there now are 21, 22 square feet, but this is, in the range of what's typically out there now. Listed at UL 1703, it will withstand 113 pounds per square foot downward pressure and 75 pounds per square foot uplift. Why different downward than upward? Well, it's all in the way it's mounted in the frame. The frame is designed so you can step on it. You see people walking on these systems when they're up on a roof. They walk right on them. 113 pounds per square foot. Generally, that's not what is going to be, unless you got a really big person up there. The pounds per square foot for 1 foot will probably be less than 113 if it's averaged out. 75 pounds per square foot uplift, and there are some wind zones that we'll see about later where this module won't work. But in most areas, and certainly wherever the wind velocity is less than 140 miles an hour maximum wind, the 75 pounds per square foot uplift is more than enough to handle it. Let's talk about roof zones. ASCE 722. It's there's 2 books you have sitting on your desk if you design PV systems, one of which is ASCE 722, the other of which is the National Electrical Code. You might have a few more, or you might have these all in electronic form, tucked away somewhere. You need some fire codes and probably some local building codes and some state building codes as well. Lots of codes apply. But in any case, let's say ASCE 722, pardon me for coughing. Next time, if I do that, I'm going to turn my audio off. Okay. In general, but it depends on the slope. Zone 1 is interior, and that's Zone 1 is interior, and it has the smallest wind load. Zone 2 is generally near the edges, and has higher pressures. And zone 3 is at corners and generally has the highest pressures. That's a general statement. Specifically, you look at the pictures in ASCE 722 in the later chapters, and they will show exactly where these zones are, depending on the type of roof, whether it's a hip or whether it's a... My goodness. Now they all have this A, this zone boundary number, and A is defined as 10% of the least horizontal dimension or 4/10 of the height, whichever is smaller, but not less than 4% of the least horizontal dimension or 3 feet. Wow. You can read that 10 times and still maybe not be quite sure what it means. But in any case, it is something that ultimately you'll figure out what it means. And it's typically going to be for a residential installation between 3 and 5 feet. And this is the boundary, and this is like as though the pressure changed instantaneously right at that boundary, which we all know it means it's going to be a gradual change, but that's where the boundary is recognized. So just need to know about it. So then we want to fit the modules on the roof. So we need to have a picture of the roof. So here's a nice hip roof picture. And because of the dimensions of the building, we're able to define A. And in this particular case, it turns out to be 3.5 feet. And that's 10% of the least horizontal dimension, which is 35 feet. Okay? Or no less than 3 feet. So we now have defined for a hip roof zones 1, 2, and 3. And we'll see what that means in a minute. But anyway, this is the starting point. You want to get these zones indicated on your roof, and there's lots of software that will do this for you automatically. You just tell it the dimensions and it'll lay this out. And then you add the modules. They might look like this, or it's very likely that the fire code is going to say, hey, you can't do them on top like that because you need either an 18-inch or a 36-inch walkway up there, depending on whether or not your array will cover more than 33% of your total roof area. So you may have to lay these things horizontally, and if you have to do that, you're only going to be able to put probably maybe 4 or 3 instead of 5 of them up there. But in any case, we're trying to keep away from the edges because if you get too close to the edge, that's an extra 50% increase in pressure. And that sometimes gets to be a little nasty in terms of mounting. But a lot of places you can do that where you can get up to the edge. But if you can avoid it, you try to avoid it. Okay, so there we go. All done. Well, sort of. Except that's where we're going to go. How are we going to mount them? We better figure out what to do next. Well, then we better calculate the wind load on them. And in order to calculate the wind load, this is what you need to know. You need to know the mean roof height, the roof zone, the risk category. What is that? Well, that's a matter of, is it residential? Is it out in the middle of the nowhere? That's risk category 1. Risk category 2 is minimal possibility of loss of human life. Risk category 3 is a little stronger and like a hospital or something. And risk category 4 is you absolutely can't let this place get managed. That's where your control center is for hurricane or tornado, where that building can't be penetrated by any means. Then you need the exposure category. And that's A, B, and C, and that's a matter of how close are you to certain, how much screening do you have from the wind? If you're right on the ocean, you're in the exposure category D. If you're inland with a lot of trees and houses around, then you're exposure category B. And what are escarpments? Are there any hills around? That makes a difference. I see something in chat. Let's see. No, that's up there. That's the instructions. I'll be watching my participant box if for questions. You need to know the size of the modules, the slope of the roof, whether it's a hip or gable roof, and how fast is the wind speed? What is the rated wind speed for the area? So the wind speed is based on data that comes in from NASA, and but it's also depending on risk category. There are different wind speed curves for different risk categories. If it's a high risk area, you're going to design it for a higher wind than if it's not a high risk building. Okay, straightforward. So here's the particular categories that I just mentioned. And category 2 is anything that's either now 1 or 3 or 4. And again, you can read this if you really want to go into gory detail on it. Order up the slides and memorize this, or at least save it as a reference. And those are defined in ASCE 722. You go to chapter 26, 29, and 30 of 722, it gives you the calculation procedure. And you look at the risk category with this wind speed contours. You determine the wind speed. You may or may not be allowed to use interpolation between 130 and 140. If it's looks like it's 135, you may need to use 140. Your local authority having jurisdiction will tell you that. So we have this formula that QZ is 0.00256 KZ, KZT, KEV squared pounds per square foot. Good units, pounds per square foot. Pressure, that's okay. That's what we need to know is the wind pressure. The 00256 it's to do with the density of wind. KZ, KZT, and KE we'll figure out here in a minute. We have to better look at what the definitions are. But as soon as we figure that stuff out, then we can get the this is QZ in pounds per square feet. And once we know QZ is height dependent. The higher you go off the ground is going to have different value. So P, the actual pressure, is going to be QZ evaluated at a height H, which is Q sub H, times a bunch of other coefficients, the KD, the GCP, the gamma E, gamma A. That's what's so fun about the ASCE uh, 722. It's got lots of really neat coefficients, and these are all coefficients that are based on field measurements and lab measurements and wind tunnel measurements, all empirical coefficients. Einstein's theory doesn't no good at all for any of these. They're all empirical. And we tend to change somewhat from time to time as those folks get better measurements. But this is what it is for the moment. QH, okay, we already talked about what QH is. Okay. And everything else depends on height, zone, module size, roof slope, and a lot of other stuff. So let's look at them a little more carefully. Okay. And this is for rooftop mounts. All right. There are other numbers that are used for ground mounts. We're not going to talk about ground mounting in this, but again, ASCE 7 has all the rules you need if you do a ground mount. So how do you figure out what KZ is equal to? Well, you look it up. It depends on the exposure. So for exposure B, which is typical residential exposure, except for places like Miami-Dade County, Broward County, and Palm Beach County, but Miami-Dade and Broward say that you can't use exposure B. You got to design everything assuming exposure C. And notice the coefficient in exposure C is a little bit bigger than the coefficients in exposure B. And D is even bigger than the other two. So if you live next to the ocean, and that's where I live, I'm in exposure D, 1.03s instead of 0.7s. Okay? So KZ, fine, great. I live in town in Orange County, Florida, 140-mile-an-hour wind. So I got a 0.7 exposure. I'm going to mute for a moment again and try to drink some water and get over that cough. All right, let's try it again. So here's your exposure categories. It comes from a table. And for residential, you don't see too many single and family detached residences much higher in height than 30 feet. So most of your exposure B, K sub Z is going to be a 0.7. Next one. Where's my cursor? Okay. So there's definition of the exposures. Okay. Now, where do we get the others? Well, we get them from ASCE 722 as well. So what's GCP? That's the exposure coefficient. It depends on the exposure, the roof zone, and the slope, and the roof type. So there are tables for them as well. Okay. There are tables for hip roofs and there are tables for gable roofs. If we happen to have a hip roof, the GCP is going to be 0.6 for downward pressures and minus 1.5 for upward pressures. If you're in zone 2, it's a minus 2.1. In zone 3, it's a minus 2.3. So that's what you multiply your pressure by, depending on the zone where the module happens to be installed. If it's flat terrain, KZT is a 1. And if it's a normal structure, KD is 0.85. What's a structure that's not normal? Well, like a water tower, for example. I haven't seen any modules on water towers yet. So, but if you have a hill, then KZT, you have to look at the table in 722 and see what it is for the particular slope you've got, and that's above and below and ahead of and behind the wind. If the altitude is less than 1,000 feet, K sub B is equal to 1. K sub B is recognizes that the atmosphere becomes less dense the higher you go. And so it drops off exponentially. And there's a nice formula in ASCE 722 that tells you how to calculate K sub E for altitudes higher than 1,000 feet. But if you're under 1,000 feet, K sub E equals 1 is a reasonable thing to use. NKZ is 0.7, as we saw for exposure B, height less than 30 feet. Slope is more than 7 degrees. This makes gamma sub E equal 1. But the area of the module at 18 square feet, that gives us gamma sub A is 0.7. So at 115 miles an hour for wind speeds, that's kind of like a New York wind speed. The product of these three coefficients is 16.6 PSF. Okay, the QH gamma E gamma A. Now we look for GCP in the effective wind area. How do you do that? Well, what's this graph you see in ASCE 722 for a hip roof with a slope between 7 and 20 degrees, which is what we have. And you notice that the logarithmic scale and horizontal, and between 100 or 10 and 100 square feet, this coefficient gets smaller. So the bigger the module, or the bigger the array, the less the pressure coefficient. And this depends on how far the modules are spaced away from each other. A lot of designers just use a conservative approach on this one and use the area of the module itself. because it still ends up with a reasonable amount and it's not totally unreasonable in terms of cost effectiveness or anything. And you also feel pretty comfortable that that thing isn't going to be there after a nasty storm goes by. So noticing at 20 square feet, uh, what's the difference between the red and a different line? Well, these must be for the different zones. Yeah, sure. Of course, this is zone one. It's going to be smaller for zone one, bigger for zone two, and a little bigger for zone three. These are the negative coefficients, the upward, the lift coefficients, the positive coefficients in zone one, two, and three, the downward gets smaller as the area gets bigger. Now let's do this, but once you're up to 100 square feet, then it levels off. So at 20 square feet for a module, you see we're looking somewhere at 2.2, and then in zone 3, and somewhere just a little over 2 in zone 2, and somewhere at about 1.2 for about 1.5 in zone 1. So again, look it up on the table, get your ASC 722 out, determine the effective wind area. All right, and I'm not going to read all this stuff because it's in ASCE 722, chapter 26, section part 2, the definition of effective wind area. And see, this says, well, okay, the effective wind area is actually could be more than the actual area of the module if you use this thing. But you need to look really carefully to make sure. And this is why a lot of people don't even mess with this, because you know that your calculation, if you don't use anything other than the module area itself, you know you're going to have a very conservative estimate and you're quite confident nothing's going to blow away. But if you're really trying to skimp and do the minimum design that's acceptable, then you can calculate this effective wind area. And your multiplier might be small enough so that you can get rid of a few of those mounts. But see, the manufacturers will say that, well, yeah, that's all well and good, but there's still a limit to how far away you can space the mounts underneath the rails, because the rails themselves can bend and give be a problem. And if there's a wind that's gusty, you can get some interesting vibration effects. So their manufacturers oftentimes put limits on the spacing of the mounts for the array anyway. And so therefore the effective wind area sometimes might allow for a wider spacing, but then the manufacturer comes in and says, no, you can't do that anyway. So anyway, but know about it. It exists, the effective wind area. All right. So now the GCP and effective wind area. Oh, there it is. What did I do? Then the final wind load comes from multiplying QH, gamma E, gamma A. And that's 16.6 pounds per square foot. See, QH, that's where you already took into account the 100 of the square of the velocity of the wind, 115 squared. And that's at the median roof height, which is in this case around 15 feet, and the gamma E, gamma A. So we got 16.6 PSF. That's nowhere near that 75 PSF that we were looking at. So we can see that this is not half bad. The final pressures in each roof zone, though, on the other hand, we have to multiply the 16.6 by the GCP factors for the zones. So wait a minute, if the GCP is big, that's kind of like a concentrating thing. Let's see. Well, zone 1, multiplying by the GCPs for zone 1, you get 9.96 downward and 24.9 upward. In zone 3, you get 38.18 pounds per square foot upward. Now, this is kind of critical because there's some modules where it depends on how you mount these things, that the rails under them, as long as the rails are mounted parallel to the short sides of the modules, then these numbers are almost always okay. On the other hand, if you mount these rails along the long side of the modules, that would be if you had a strange situation where you needed to mount these modules, like maybe on that first layout, if we wanted to lay them in landscape instead of in portrait, then the modules in landscape have a lower rating, so you need to be careful about that. You get a lower uplift rating for landscape than for portrait. And that sometimes that low landscape rating is at 33. So you notice zone 2 and zone 3 landscape modules with rails parallel to the long side is not okay. Again, this is a very specific thing. It's getting really picky, but it's something we see once in a while, and we would pay very careful attention to that in our designs. So if we, this design uses A equals 18 square feet, but if we use the fancy definition, then A would be 92 square feet, and that would change the value of GCP and make it lower. So on the other hand, when you're mounting modules in landscape, normally you're not going to have more than about 3 in a row. So that total area is maybe going to be 60 square feet. And it wouldn't be 92 square feet because there are just not enough modules in a row. But here we got 7 modules in a row, so that gives an A of 92 square feet. Okay, so there we go. We've got a wind load. So what do we do with it? We need to figure out, not going to check the time here, 3:27, okay. We're okay, we're gonna make it. We put in some rails and we put in some attachment points. Lots of good commercial stuff out there. You just talk to your suppliers and they'll tell you what they've got available. And the manufacturers have lots of good data sheets to go along with their rails. The rails are designed to last 25, 30, 40 years. The mounting clamps, typical clamp will can hold at least 800 pounds and maybe more. Although some of the standing seam metal clamps are 500 pounds or less for a single point pull. But anyway, you come up with a maybe this will work kind of design. Then you run the calculation and see if it really will. You can see where the zones are, the rails, the attachment points. You see the amount of cantilever there, or the amount where the how far the module hangs over the edge of where it's connected. And all those things are required to know there's a maximum cantilever allowed for most modules, and typically somewhere 16 to 24 inches for a module that has a width of about 40 inches. Again, depends on the zone on the roof and the wind speed and the type of roof. So here's a possible design. Let's take a look at how this works out. Is it going to blow away? How long do the screws have to be? Well, 18 square foot module. Top row has 54.9 square feet in zone 1 and 35.1 square feet in zone 2. So that we can calculate the total uplift then is the amount in zone 2 times plus the amount in zone 1, 2,592 pounds. Middle row has 3,676 pounds total uplift, and the bottom row has 6,071 pounds total uplift because it's got more modules in it. And it's also in a different wind zone. So, and it's got some area zone 3, that's a little bit more pressure. So you calculate the total uplift for each row, and you can see how this could easily be computerized if you simply say, hey, this is zone 1 and the wind speed is this, and it runs, so it gives you all the numbers. So this may look like a lot, but if you do this for a living, you're going to have software that does it almost automatically. It's very nice several very nice pieces of software that'll do this. So in the top row, if we take the average uplift per mounting point, you notice that you tend to shift your mounting points a bit to the zones 2 and zone 3 if necessary to make sure that none of them would have too much of an uplift. But we're doing averages for the whole string here. And notice that the worst case is the bottom row at 289 pounds for each one. So the question is, how far does a screw have to go into the truss in order to be able to withstand 280-pound uplift, 289? Well, if you use a 5/16 lag screw, that's the most common type used. Sometimes a 1/4 inch is used, but most commonly it's a 5/16 inch stainless steel screw, somewhere between 3 and 4 inches long. How far does it have to go into the truss? Well, your wind, if you look at the reference for this, whoops, what happened? The wind load guide for southern yellow pine from the lumber industry and white spruce and Douglas fir tells you if you have southern yellow pine trusses, which we have down here, then a 5/16 inch screw, an inch embedded into that truss gives you 332 pounds of holding strength. A lot of the mounts have 2 screws in them. So that would be twice as much if you have 2 of them screwed in that far. And some of the mounts have 4 screws. So you can see that for the most part, there's not a big issue in having enough holding strength. And there are some cases where you can actually screw down into the decking with 4 screws and if you have enough clamps, you have a reasonable way of holding down without having to actually even get into the trusses. Okay, and this is a safety factor 4. Okay, so much for the structural part. Let's do electrical. And the electrical will go a little faster. There are not quite as many variables here. We're just going to do some designs based on the systems we had looked at earlier. Okay? So we'll do a microinverter design, we'll do a power optimizer, and a string inverter design. Okay? Every single one has maximum power point tracking, and every one incorporates rapid shutdown at the module level. So once the emergency responder flips that switch that says no more power from the roof, within 1 foot of the array on the roof, the power's down to nothing. There's no more voltage left. And otherwise, and that's what the rapid shutdown's all about. So, come on. Okay. UL 1741 or 1547, sorry, UL 1741, which is based on IEEE 1547 standard 20-18, in the most latest version. They did have a 2018 addition to it, or 2020 addition. Says the following. Have to have good sine wave, less than 5% total harmonic distortion. That means it needs to be a nice sine wave. Not much little bumps or dips or ripples in it. And the specific harmonics, it specifies the maximum amplitude for any odd or even harmonic of that 60 hertz sine wave. Says that the utility goes too low in voltage, it has to shut down. If the utility goes too high in voltage, it has to shut down. And same thing, if a utility goes over or under frequency, it has to shut down unless you have a deal with the frequency utility. If you've got a 200 megawatt utility system and the utility frequency starts going down, the last thing you want to do is turn off that system, because that's going to send that frequency into a nosedive. You want that thing to stay on to make as a stabilizer for the system because the frequency goes down when the system tends to get overloaded. Okay, so this is a part of the deal with the utility. Anti-islanding requirements means it just has to shut down if other PV inverters are still going on. Your inverter has to shut down. Inverters have to know the difference between an inverter and utility. And one might think, well, that's really complicated, but in fact it isn't because inverters operate as current sources rather than voltage sources unless they are operating under emergency situations where they actually switch automatically to become a voltage source. Those kinds of inverters are very special. They're called hybrid inverters. But the ones we're talking about here, they don't do that. Okay. And we have the option of utility control of a huge system for more better support of the grid. Or conceivably, they could have control of a whole lot of smaller systems to have better control of the grid. So let's design a microinverter system. My goodness, here's one right here. That looks familiar, doesn't it? How are we going to design that thing? Well, here's the rules. We match microinverter to the module. So that means the microinverter is going to tell you the maximum voltage you can have at its input. That's DC. And the maximum current that comes from the module. And as long as your module, open circuit voltage and short circuit current don't exceed these parameters for the microinverter, and most of them don't. The only difference is sometimes you might have a 96 cell module and then your microinverter has to handle more than 60 volts. But most microinverters are rated at 60 volts. Okay? And here I say 60 cell modules, but that's the point. A 60 cell or a 72 cell module is not going to put out more than 60 volts almost no matter where you're going to put it. So then the rated microinverter current, obviously, we as we said before, the currents from the modules add at the output of the microinverter. So typical microinverters will put out 1 amp. That's the older ones. 1.21. Quite a few of those out now. 1.35, 1.45. And 1.58, you could add to that as well. 1.58s are now coming out, becoming a little more popular as well. Since modules rarely generate rated power, that means the microinverters can handle modules with power ratings that are 150% of the microinverters themselves. So a 345 volt ampere rated microinverter can have a 460 watt module connected to it. And we're going to show a picture of that later and show what difference that makes to the performance of the system, because most of the time that module is putting out a whole lot less than its rated power. Okay? So a 290 watt module is sometimes even used with a 440 watt, a 290 watt microinverter is sometimes used with a 440 watt module. Not as often anymore. People tend to like to use slightly bigger ones, but a 290 will work with very few losses. So matching the module to the microinverter, here's the module, here's the microinverter. And you look at the orange stuff, the maximum power point voltage is 41.7. That's clearly well within the range of the microinverter. And everything's within range here, okay? And again, just to prove it, you can look at this later, but take my word for it. You match the modules to the microinverter. You select the rest of your components. Here's the module. Put the modules on the roof. 13 per circuit. So we're going to have 2 different circuits, 12 modules each. Might possibly look like this. But notice Are these 12 modules each? Yeah, it is, isn't it? There's 11 and we add 12, so it's 12 and 12, nice balance. Although that number one module in the second row, one might say, well, why didn't you just make that a number two? And wouldn't that still be okay? Well, the problem with that is then if you made that a number two, you would have 3, 6, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, this is 24. And so we could have 13 and 11 because the maximum number we can have is 13 in a circuit. But we decide to make it even, so okay, we'll do it like this. This is one acceptable configuration. Not the only one. As long as we don't have more than 13 in a circuit, because in a 20 amp circuit, the maximum microinverter current can be 16 because the circuit itself and the overcurrent protection has to be rated at 125% of the maximum circuit current, which is 16. If you have a 20 amp circuit, the maximum current allowed is 16. So if you divide that by the maximum inverter output, 1.21, it means no more than 13. Okay, pretty straightforward stuff, isn't it? Okay, and again, if you have a copy of the slides, you'll have all the rules at hand. So in this case, we have 14.52 amps per circuit, 12 times 1.21. That's well below the 16 amp limit, so we're good. The array is 9,600 watt DC rating. That's important as far as utility is concerned, because they tend to say that if your array is a little over 11,000 watts, then we're going to have you classified as a higher class one, as class two instead of one, and you might have to buy some extra insurance on it. You might have to have an external disconnect for the system. So under 10,000 watts of AC output, and this is going to have under 10,000 watts of AC output because we've got 24 times 290 watts, and 24 times 290 is only 6,960. So we're well within that limit. Microinverters are all listed. Cabling is listed, all provided by the manufacturer. So everybody's happy on that. Combiner box at ground level. And here's your connection right here. Coming down from the roof, the two circuits to the combiner box. And there's a data thing in there that collects and talks to the modules on the roof and asks them, it figures out exactly how each one is performing. And in fact, it's great because if something goes wrong, this gets reported to the owner, wherever the owner might be. And even the manufacturer of the microinverter probably has a pretty good idea of what that microinverter is doing. Unfused disconnect might be optional. And then where do we go from here? Well, there's a number of different ways. This is one way. As long as 125% of the photovoltaic current, which is 36.3 amps, does not. Wow, why am I coughing like this? NEC, National Electrical Code 705.12B32 says if the output of PV, that is 125% of the PV output current, plus the rating of the main disconnect does not exceed the rating of the bus bar, well, I got it cut off. You got Sorry, folks. I thought I was over the flu. I haven't talked for 2 hours for a while, and I guess my throat is still reminding me. So, in any case, this is called the 120% rule. So 120% of 200 is 240, and 200 plus 36.3 is less than 240. So as long as you connect at the end of the bus bar opposite the main circuit breaker, then you can use this method of connecting. If, however, pardon me one more time. Okay, back again. Wish me luck. If the 120% rule doesn't work, there's a couple other possibilities. So let's assume that's not the case. If it's more than 100% of that, or there's possibility that there's no room for that extra circuit breaker, then we can use a thing called a supply side tap, which is in NEC 705.11. You see what's happening here. We put in a fused disconnect, and this has to be service rated, by the way, probably something like 24,000 amp fault current rating. But we're tapping in ahead of the main circuit breaker here. And you just follow the rules for that, and it's okay to do it this way. If you can't get to the line side of the main circuit breaker, that's also a possibility, because sometimes it's just a bus bar between the meter and the main and distribution, the bus bar of the main panel. Then you can do this, called a load side tap. So you got your main disconnect, and then you tap between two circuit breakers. This is 705.12B33. And keep in mind, what's coming out of that photovoltaic system is current, and it is first going to be used by your photovoltaic by your distribution system uh, in the panel. So your loads at the location of the installation will get first shot at what's coming out of the solar system, and it will simply go there, and the utility doesn't have to provide as much. Now, how can a silly little PV system overpower the utility? It's very simple. It's the voltage. The PV system simply operates at a voltage simply high enough to make sure that the current always comes out of it. And it ends up at a voltage equal to whatever is there at that tap condition. And that voltage is less than the voltage that the utility is trying to use to send it through to meet the needs of the load. So it's a thing that adjusts itself automatically. And the first power that goes to that bus bar is from the solar. And anything the solar doesn't need then is made up by the utility. Okay, so there's that connection. In that 150 amp circuit breaker at the top of the other says that the sum of the current from the solar plus the utility is still not going to exceed the rating of that panel. Here's an optimizer system. How are we doing on time? 10 minutes. It's about right, because from here on it gets pretty simple. Optimizer Notice they're in series. And we have to match the optimizers to the modules. Here's your rules. We talked about them before, and here's the design rules. So once again, all in a nice little package here on this slide if you want to pay a lot of attention to the optimizers. So as long as your array rated power is not more than 155% of the rating of the inverter, you're okay. And once again, because normally total output of the array is not going to exceed the capability of the inverter to invert it. But if that just so happens, the inverter has the capability of telling those optimizers, you got to back off and limit the input to my rated power, which might be 7,500 watts, might be 11,000, but whatever the rated power of the inverter, maybe it's 33,000, who knows, it's for a bigger system. So the inverter talks to the optimizers, make sure they don't give it more than it's capable of handling. It's just that straightforward. Matching the module to the optimizer again, I'll just show this, have you take a look at it. This is a typical combination of module and optimizer. Manufacturers are very forthcoming with telling you if you're going to buy this module, then you need this optimizer to match it properly. But when one's been doing it for a while, you get pretty used to what's out there, and you pretty much know exactly which one you want to pick to match the module you're using. Once in a while, you'll see a system with 96 cell modules where the voltage can go exceed 60 volts at the output of the module. And then the rated input voltage has to be more than 60 volts, so the optimizer needs to be ready for that. Okay. So here we go. The array power is 9,600 watts. So here's our design. 2 circuits of 12. So that means maximum power for either circuit. 400 volts, 15 amps. That's 6,000 watts. But it's not going to go more than 6,000. That's what the maximum that the optimizers can deliver. Maximum input power then is 11,800. Notice that's twice 6,000. Maximum input voltage 480, and the inverter controls that. Nominally, the inverter is going to let it be 400, but if it's a nice, cool, sunny day and the system wants to put out a lot of power, then it will raise its input voltage accordingly to make sure the input current doesn't exceed 15 amps. In this case, the maximum is 20, but the optimizers themselves probably don't want more than 15. So the inverter itself wants no more than 20, but that if you have 2 strings of modules, then each string wouldn't want to have more than 10 amps. So output voltage 240, output current maximum is 232. Why 32? That's a nice number. Well, 125% of 32. That matches up perfectly with the 40 amp circuit breaker and some number 8 wire. 125%, there it is right there. Weighted efficiency of this thing, this is what's really impressive, is 99% efficient conversion of DC to AC. That is really good. Ungrounded input, that's important. The array itself, there is a plus and a minus in the array, but neither the plus nor the minus is actually grounded. And that's required because it's a transformerless inverter. And the electronics then have the array floating so that they can ground the neutral of the 240 volt, 120, 240 volt output of this inverter. What else? Just some observations about modules and optimizers running independently. And the circuit lengths can be different lengths. Just as in the case of the microinverters, the only thing with the microinverters is you can have one of them, whereas there is a minimum number of modules in a optimizer circuit. And in this particular case, it's determined by the fact that none of these can run at more than 60 volts. And if you're operating at 400 volts, then 400 divided by 60 is 6.67. So that means that you need at least 7 modules so that the output of any of those optimizers will not exceed 60 volts. So somewhere between 7 and 15. Okay, what are the circuits? Maybe they'll look like this. Who knows? Just like that. Bingo. Up on the roof, plug it in. There's your electricity. What we got down the ground, same stuff. Inverter. Do it that way or that way. What happened? Or that way. Either way, same as with the microinverters. Now, we were talking about the DC to AC ratio thing, and here's a graph here. If we have a 290 watt microinverter with different module ratings, and this is a 290 watt microinverter, and we're looking at the annual kilowatt hour total energy production, okay? So this is a simulation with the this is no longer the National Renewable Energy Laboratories. Of course, it's the National Laboratory of the Rockies, but it used to be Lanarel back in the good old days when we believed in solar. In Orlando, south-facing module, 18-degree tilt. Here's the deal. This is the output of the annual kilowatt hour output of the microinverter based on the rated power of the module connected to the microinverter. And you can see this almost linear. Less than 1% difference between the lower power and the higher power. So therefore, it's basically saying that for the most part, the system does not run anywhere near having full sunlight directly shining on the module. And if it is directly shining on the module, usually that means it's going to warm up the module and it's going to run at lower power before, as you saw from that graph way at the beginning. Okay, if we just have maximum power point tracking at the inverter, and there are systems like that, a number of them, that are relatively popular, maybe 20% of the total that are done. This is a design procedure. I'm going to run through this very quickly because we're only 1 minute to go, but the procedure is here straightforward. You got to be a little more fussy here. First of all, you got to make sure that for any one maximum power point tracking input in the inverter, and oftentimes now the inverters have more than one maximum power point tracking input. For each maximum power point tracking input, all of the modules have to be facing exactly the same orientation. The string lengths don't have to be identical. There's a maximum minimum numbers per string. Okay, so if we have that module, I guess we're running a little late because of my post-nasal drip issue. 245 to 600. This is a calculation procedure. I'm not going to explain it right now, but again, if you're interested in this, send a note to our host, and he'll forward it to me, and I'll give you a reference where you can look this up. I know a guy who wrote a book on this stuff, and it's got all of this in it. In fact, he lives at the same address. Oh, it's me. So in any case, it's all there in case you need a reference. Hottest cell temperature, it's easy to calculate. How hot is this? What's the lowest voltage this thing's going to operate at? We need to know the highest and the lowest in order to determine the string lengths, okay? So here we go. Again, don't try to read this fast. It's there in case you need it. You've had a saturating effect of a lot of material in 2 hours, but it's all there. Almost everything you need to know is there. And more information on, of course, is available from other references and particularly from manufacturers' data. That young lady fishing there on the left-hand side is now the mother of my great-grandchild, and her brother to the right is a practicing mechanical engineer up in Minneapolis. So they'll appreciate whatever we can do to make a better future for them. And I happen to be convinced that photovoltaics is one of the important parts we need to add. Not the only, but one of the important contributors. And we're doing it. And whatever we're not doing, a lot of other people around the planet are doing, and doing it very rapidly right now. So we've got a minute or two. If anyone has any other questions, any comments, I'm going to open up my, there's some comments over here, Q&A. Any advice and codes for ground mount panel? Yeah, the ground mounting instructions are very clear in ASC 716. It's just a different chapter. But they're typically mounted with ground screws. The only thing is you got to be really careful what's under the ground. If you got a lot of rocks or things, then you can have some interesting issues. So actually, ground mounts are much more complicated than roof mounts, depending on the ground. If you got a lot of rocky ground, it's not particularly easy to get those mounts in there. People talk about these fields of solar modules. Well, the interesting thing is most of those ground mounts just screw right in. And if 50 years we need that field of solar modules for something else, you unscrew them and take the modules on, get everything out of there and build whatever you need to build or grow whatever you need to grow. And lots of folks don't realize that, but it certainly is the case. Now, let's see what else we got. Barbara, wind load and structure requirements of ground mount. Yeah. Again, same thing. Just find it in it's all in ASCE 722. Any other questions while I've got the Q&A box open? Okay, well, I apologize for my cough coming back. I had not anticipated that. I thought it was better, but hopefully we got enough information here that it was a worthwhile use of your time this afternoon. And like I say, if any further questions you might come up with, if you are interested in going further in, um, if you'll contact me through the host, I'll happily respond and do the best I can to answer whatever questions you might have. I've been in the business for a while, got lots of, or you can just send it to Roger, ROGER messenger, MESSENGER 501 at gmail.com. I guess I could type that too. Let me just type that answer. Oops. Okay, there's contact information. If you want to just contact me directly, it's fine. I will try to get back to you within a day. I see something in chat. I think that's probably our host saying, hey, I want to go have dinner. Okay. Good luck on your system, Ed. Send me a note. Tell me how it works when it's done. I think you'll be very pleased with it. And note that in the chat box, the instructions are there for getting your documentation of attendance and all that stuff. Okay, I guess we're all set. Thank you for your attendance and any feedback, always welcome. Anything you wish you'd learned or wish I hadn't spent too much time at, anything like that. I taught at university for 35 years, so nothing better than feedback from students. Uh, I tried to pay careful attention then, and I try to pay careful attention now. Okay, Mr. Host, I believe we can call it a day.